Welcome. In this lecture, we're going to start a very cool topic that is the introduction to Fourier analysis that we're going to see in this course. Now, be prepared for this because this is very deep. This is mathematically very deep, this is conceptually deep, and this is powerful, okay? So pay close attention to all that we're going to see now because it's opening the doors to a new field of mathematics that you haven't seen before. We'll see. All right, let's go historically. Historically, we go all the way back to the Napoleonic Wars. Napoleon, when he invaded Europe and the north of Africa, he brought with himself many experts in many fields, scientists, mathematicians, archaeologists, historians. Famously, for example, in the expedition to Egypt, invasion of Egypt, but it's called expedition to Egypt, whatever. In the expedition to Egypt, he brought Champollion. Champollion was the person who found the Rosetta Stone. The Rosetta Stone had a text in hieroglyph, the same text in Sumerian and in ancient Greek. Now, having the ancient Greek, Sumerian, and hieroglyphs allowed Champollion to come up with the first way of translating hieroglyphs. Hieroglyphs were not, the knowledge about what hieroglyphs actually said was lost in history, and it was only recovered after finding the Rosetta Stone. That was when Napoleon brought Champollion to Egypt. Now, also, Napoleon brought Fourier, mathematician, physicist. Now, Fourier didn't really find a Rosetta Stone there, but he found one thing, that he hated the weather there, hated the heat, hated the dry weather. He really hated it, couldn't stand it. He was kind of like really wanted to go back to France. Now, out of that trauma with the weather, things came up. Now, Fourier got obsessed with heat and actually came up with the modeling of conduction, what is called the heat equation, that we will actually see when we study PDEs, introductions to PDEs, right? But to solve the heat equation, Fourier introduced a new tool, the Fourier Series, and it was really outrageous when it was introduced. Let's see what Fourier said when he introduced it. Outrageous claim, because he provided no proof whatsoever. He dropped it. Imagine all the mathematicians and everybody like, what? It took Dirichlet and several other people after Fourier to actually prove all these things and make them rigorous. So let's begin with exactly what Fourier said. Consider a function of x defined in the interval x minus pi to pi. Why minus pi to pi? Irrelevant. We're going to extend it to any interval, no matter how big, no matter where you put it, later on. But this is the original way it was introduced, okay? So bear with me. Imagine a function defined in the interval minus pi to pi that is piecewise continuous. What does that mean to be piecewise continuous? Well, you want the function to be continuous, but you allow for it to have jump discontinuities. For example, something like this. Something like a square pulse in a way, if you want. So you get the function is 0 here, and then jumps to 1, and then jumps to 1. That's discontinuous at these points, right? Has a jump discontinuity, but that's okay. It's still piecewise continuous. In fact, you can have as many discontinuities, jump discontinuities as you want, as long as it's not infinite. A finite number of them, okay? And that is piecewise continuous. All right. Then it says, its periodic extension over the entire real line, that means the function itself in this interval, but also a repetition of the function many times, can be expressed as a linear combination of sines and cosines as follows. And write this. The function is equal to infinite sum of an infinite number of cosines with increasing frequency, and is going up, and sines with increasing frequency. And also A0. Now, A0 is a constant term, but keep in mind that's also a cosine term, because when n is 0, cosine is 1. Now, if that was a consistent notation, this thing should have been A0, not A0 over 2. Why do I add the over 2? Well, the reason I add the over 2 is related to normalization and to make things simpler for the first time you see Fourier analysis. This is common in engineering too, having the 2 in there. But it's just a convention. So I add a factor 1 over 2 in the redefinition of the A0. Then that's nothing. But again, it's a sum of sines and cosines. It's a sum of sines and cosines. And then Fourier said, with the coefficients, an and bn, which are numbers, those are the coefficients, right? Given by these integrals. Integral of the function times the cosine for the cosine coefficients, divided by pi, and integral of the functions times the sine for the sine coefficients. And then Fourier said, if the series converges, I don't even know if that series converges. Sometimes it may not. But if it does, he says, the series converges to this. This is the function. When the function is continuous, these are the lateral limits. X coming from the right plus x coming from the left divided by 2. So if it's a point here, this is f of x exactly. This is to tell you what it converges to in a discontinuity. So what is the value of the series in here when the function is discontinuous, doesn't have a value? Well, take the lateral limit from the right, which is 0. The lateral limit from the left, which is 1. Take the average, so 1/2. That is why I said, when I define the Heaviside, that the good definition of the Heaviside would have the value 1/2 in the discontinuity. But that is something we will see later, okay? Anyway, what Fourier is telling me is that if the series converges, it converges to this expression, which is the function itself when it's continuous, and in the discontinuities, the average between the lateral limits. And that's it. Bomb dropped. Fourier does a mic drop with that, says it and leaves. And all mathematicians are like, what? Now, this is extremely deep, and consequences, wow, okay, let's see. To begin with, just waving hands a bit before getting a little bit more into the relationship with algebra. Consequences. Any function, in this case minus pi to pi, can be understood as a sum of sines and cosines of increasing frequency. It's like, right, so I can think of any signal between minus pi to pi, any function between minus pi to pi as a sum of things that oscillate with a pure frequency, many of them. Wow, there are frequency components to a signal. Interesting. Second, now we're dipping our toes into a new field of mathematics that you're starting to see, called dipping toe into functional analysis. We're doing this slow dipping into functional analysis, understanding the relationship between algebra and calculus. Let's see. Let me recall for you some of your linear algebra that you have seen already. You know the notion of an orthonormal basis, no? Let's see, of R2. An orthonormal basis of R2, E1, E2. I don't know, think of R2 as a plane, and then we have here E1, E2, right? Then I know in an orthonormal basis, orthonormal means that the vectors are orthogonal. E1 times E2 equals E2 times E1, where this is the inner product, right, equals 0. And then E1 times E1 equals E2 times E2 equals 1. That's what it means to be an orthonormal basis. If you want to write it in a compact way for any dimension, now that you learned what the Kronecker delta is, remember, you can write advanced note. EI dot EJ is equal to delta IJ, right? Remember, this thing is 0 when I is different from J and 1 when I is equal to J. Is this still the same collection of these equations? And actually you need dimension. If it were dimension 10, it would be the same equation. Anyway, whatever. So that's an orthonormal basis. And one thing that we learned, right, is that any vector V can be written as 1, 2, 3, let's say, 3 times E1 plus 2 times E2. It can be written as a combination. V is a combination of some number of times E1 plus some number of times E2, and those are the components of the vector. Usually you represent this in this basis as V1, V2, right? So this thing is the length V1, and this thing is the length V2, and you see V1 and V2 are the projections on the axis of V. Now, how do I get given the first, any vector in R2 can be written in terms of a linear combination of E1 and E2, elements of the basis. That makes a vector space, huh? All right. Now, what are the value of these numbers, of these components? How do I find, if you give me the vector like that, how do I find the value of the components? Well, that's easy, right? The inner product of V with the elements of the basis, if I substitute, let me substitute this here. So V1, E1, V2, E2 times E1. If I do the inner product of V with the first element of the basis, what do I get? Well, I get V1, E1, E1 plus V2, E1, E2. And because it's orthonormal, this is 0. and this is 1, and it gives me V1. Indeed, the projection of V on the elements of the basis, the inner product of V and the elements of the basis, gives me the components of the vector, right? Same with the second component. That's something that you've seen in linear algebra. Now, let's look at this. This is saying that the functions piecewise continuous between minus pi and pi form a vector space, and the sines and the cosines are a basis. I can express the function as a sum of the elements of the basis, and an orthonormal basis of that. This is big. So this is, so the space of functions between minus pi to pi has everything that you studied in algebra, only that is infinitely many elements of the basis. It's an infinite dimensional. Instead of two-dimensional like R2, two elements of the basis in an orthonormal basis, we have infinite elements of the basis. It's an infinite dimensional space. And it's also something called a Hilbert space. It's got an inner product. And the inner product and a distance that comes from the inner product, a notion of distance like in R2. What is the inner product? Well, look, the component AN is the same as the Vn for the vector, right? So the component, if the vectors are the cosines and the sines elements of the basis, these things are the projections. You see, this thing, V1, is a V times C1. The same way AN would be f of x inner product, whatever that means, with the cosine of an x. And what is the inner product? Is defined from this integral. So this is an inner product. This, the same way that you had the dot product, for infinite dimensional spaces of functions like this, we have another inner product, which is f of x times cosine of an x. That's the inner product. So I can define this inner product. Let me just write it like this. I can define the inner product between f of x and the cosine of nx. That's an inner product. And the inner product, I'm defining it as, in this case, 1 over pi minus pi to pi fx cosine nx dx. This thing is an inner product. Again, this might be a little bit difficult to wrap your heads around the first time, but please admire it and think about it and ask me questions in the review sessions. You're not supposed to just be enlightened by words that I say. You're supposed to, what is this guy talking about? What? And then we go to the review sessions and talk about it. Because yes, indeed, the functions between minus pi and pi, and in general, we will talk about the functions in general, but let's wait for it, form a vector space with an inner product, and the basis for the vector space between minus pi, of the function between minus pi to pi, is the cosines of an x and sines of an x, and it's a freaking vector space like in algebra. Algebra and calculus, two different manifestations of the same thing. I promised to tell you something about this, that I'm waiting for you to actually see diagonalization. So because I'm not sure if by the time you watch this video you would have seen diagonalization, I'm going to wait until almost the end of the course to reveal a little bit more about this connection between algebra and calculus, and think of functions as elements of an infinite dimensional space to which we can do algebra on. And when you do it, you do it in calculus and algebra and calculus. And it's like the two things are intertwined and are the same thing. Anyway, that will have to wait. For now, think about it and come talk to me about it, okay? Now, this is pretty outrageous though. I just told you all that and it's like, are you expecting me to believe it? You don't have the tools to do the proof yet? But what we can do is do an example and you can go to the computer and check if it's crazy or not for that example, and that will give you strong arguments to at least see, okay, there's something going on here. All right, let's do it. Let's do this example I have here. Let me clean the board. All right, so let's do this example. We have a function here that has this expression. It's a piecewise expression, and you can tell the function is 0 from minus pi to minus pi over 4, so 0 up to here. Then 1 from minus pi over 4 to pi over 4, all right? And then from pi over 4 to pi is 0 again. Always in these problems, recommendation number 1, always draw it. Draw the problem, always. It will help you, okay? All right. Let's compute the Fourier series for this function, piecewise continuous. I mean, it's discontinuous, you see, but it's piecewise continuous, okay? From minus pi to pi. All right, so let's get to it. Always, in these cases, you need to compute, then my recommendation is always that you compute the A0 independently. Why? Because the A0 is the limit of AN when it goes to 0, that is true, but it's always safer to compute it independently, okay? All right, let's do it independently, as we were saying. So, and then we will check that the limits coincide. In some cases it's very simple, but in others it's difficult. As an algorithm, I would say first compute A0, then compute AN, then compute BN, okay? All right, let's compute A0. What is A0? All right, so the integral is 1 over pi, integral minus pi to pi, f of x, cosine of 0, which is 1, dx. That's easy, huh? Because from minus pi to minus pi 4 and from pi 4 to pi over 4 to pi is 0, so this is the same as 1 over pi, integral minus pi over 4, pi over 4 of 1 times dx. All right? So this is 1 over pi, and this integral here is pi over 2. So pi over 2. All right, so this thing is 1 over 2. That's A0. Okay. Most of these integrals are done by parts. I'm not going to be doing them, but I'm going to give you some directions, some tricks to do some of them very fast. Now, let's compute AN. AN is 1 over pi, integral minus pi to pi, f of x, cosine nx dx. Now, of course, same as before, this is 1 over pi, integral substituting the f, minus pi over 4 to pi over 4, because it's 0 outside of that environment, and it's 1 elsewhere, cosine of nx dx. All right, so that integral is very easy, because this thing is the integral of 1 over n pi sine nx evaluated from minus pi over 4 to pi over 4, sorry about this, to pi over 4, all right? And this thing is twice n pi sine n pi over 4. That's the AMs. That's the A0. And now the BN. Bn is the integral of 1 over pi minus pi to pi, f of x, sine of nx dx, same as before, this is 1 over pi. Now actually, I don't think we would need to do that, and I'll tell you what tricks would make you do that fast. I know the result is 0. Without doing it, I can see the result is 0. And we will see in a minute, okay? But for now, let's do it, because the first time we do it, this is minus pi over 4 to pi over 4 sine nx dx, right? And this thing is minus 1 n over pi, the cosine nx, all right, from minus pi over 4 to pi over 4, and this thing is 0. All right, so that means that the solution is f of x, it's equal to A0 divided by 2, substituting here. Maybe I should write it. I'll write the expression and then I'll write the substitution. So it's f of x, it's equal to A0 divided by 2 plus sum over n equals 1 to infinity of an cosine nx plus sum n equals 1 to infinity of bn sine nx. All right, so if I substitute the coefficients, 1 over 2 over 2, 1 over 4, okay? And then plus sum n equals 1 to infinity of 2 n pi sine of n pi over 4, and then the cosine, this is the an that we just computed, and the cosine of nx, and this is f of x. All right, I can erase this. This is f of x. This is the final result. All right. How outrageous. So this function, that is a discontinuous function like that, and it's square. There's no oscillations that are smooth. This is freaking square. Well, it's an infinite sum of cosines. Let's keep in mind that expression. No, actually, let's go right now. Let's quickly go to the computer and check if this is true. If this function here is actually reproduced by these infinite sines of cosines with these coefficients. These are numbers, huh? When n is 1, this is the sine of pi over 4 times 2 divided by pi. So these are numbers. All right, the only dependence on x is in here, in the cosine. So it's a bunch of cosines, there's not even sines in it. All right, let's see it in a computer. First of all, we need to convince ourselves that this is right, that this is correct. Let's do it. All right, so we're gonna see the demonstration that the Fourier representation that we computed for this piecewise function that we saw on the board actually corresponds to the function. So we have here the function defined as we saw. So this is the function list 1 when x is between minus pi over 4 to pi over 4, and then 0 otherwise. That's the way you write it in Mathematica. First condition and then second condition if the 1 is not fulfilled. If we plot this function, we're going to see that indeed this is a function that is 0 and it's only 1 starting from minus pi over 4 to pi over 4. All right, so let's see. Here we have the Fourier representation. So this function is certainly not a sine or a cosine, right? It's a square pulse, right? Now, this function here, it's the sum of the series from n equals 1. You see, this is the same series that we computed in class. It's the sum from n equals 1 to nm. nm is 1. Okay, so we're going to be adding, first we do it with one term. What happens with one cosine term? And we see that the function is a cosine. It's certainly far from being a square, right? It needs to be a square. I mean, roughly kind of captures the domains, but it should not be 0. But it's certainly very different from a square. You see, this is the series we found in class. I mean, we are supposed to get exactly this function with the square going like that for n going to infinity. Let's see what happens when we add two of them. Okay, kind of. It's getting there, right? But it's difficult to imagine how just adding, you know, what we're adding here is just cosine of an x with coefficients. This is a number. You see, this is a number. Depending on the value of n, this is a number. And these are just cosines. We keep adding cosines, but let's see what happens when we add 3. Okay, well, you see how these things are going to 0, kind of, outside of the interval. Let's see what happens when we add 10. Oh my God. As we are adding, you know, that's looking more like the square pulse, right? I mean, still far from it, of course, it's cosines only, right? But what about 20? Oh my, how about 100? That may take a little, oh my God. You see how we are getting more? In fact, it's kind of nailing almost everywhere. Let's do 1,000, even though it will take a little bit more. And you see how it's nailing almost everywhere, except for the discontinuities, and discontinuities is trying a little bit harder. Let's see what happens when it does 1,000. And again, that takes a little bit, but there you go. As you see in 1,000, you start seeing how near this is 0. It's almost cancelled everywhere. When we get to the discontinuity, it's got kind of horns, but you see how it's certainly reproducing the square pulse that we have here. Right? It's really, really approximating that square pulse. And the fact is that if we add the infinite number of them, we will get the square pulse. Any finite sum will have troubles reproducing these horns. And that is what we call the Gibbs phenomenon. And we will talk about it in 2 videos. But you can see, right, how as we keep adding, we go from 1 to 100, which is relatively fast. You can see how it's reproducing the function. Indeed, when it goes to infinity, I haven't shown you the theorem, but when n goes to infinity, it reproduces. I mean, the computer will take forever to do it and doesn't have precision to do it. But you see that this is exactly the same function, and it's getting closer and closer to the function and reproduces exactly the square pulse function that we have here. I mean, here it doesn't plot the vertical lines, right? Because Mathematica doesn't do that for the function. But you see that this is the square pulse, the same one as this one. So certainly the Fourier series does reproduce the function. All right, let's go back to the board. So we saw in the computer that indeed this infinite sum of cosines, in this case there's no sines because Bn is 0 for all n, this infinite sum of cosines gives me exactly this square pulse function. Now, before we move to the next thing, which is extending it for functions that are not defined from minus pi to pi, right? Periodic functions in any periodicity interval, we're going to discuss a couple of tricks of calculation, one subtlety and one trick to do integrals fast, in this case. The inner products fast, all right? Now, remember that what we did, and we will be doing that all the time, is calculate A0 first. And when we calculated A0, how did we do it? Let me remind you. A0 was, from the definition here, 1 over pi, integral from minus pi to pi, then f of x, cosine of 0, because n is 0, so 1, dx. And then I substitute the function, and I got 1 over pi, integral from minus pi over 4, because it's 0 outside that interval, to pi over 4, of 1 dx. And that gave me 1 over pi, and then that gave me pi over 2, so 1/2. But I could have computed it as well as this. A0 is indeed the limit when n goes to 0 of an. So we substitute, and we get that this is 2 over pi, I take the constant out, times the limit when n goes to 0 of sine of n pi over 4 divided by n. Now this is an indeterminate limit, right? 0 over 0. You can do L'Hopital, feel free to do L'Hopital if you want. I'm not going to do L'Hopital because it's much faster to do a Taylor expansion. The sine of x goes like x plus things of order x cubed, and I don't need more than that. So this is 2 over pi, 2 over pi, and then doing the limit when n goes to 0 off, and then the series tells me first term only, n pi over 4 divided by n. Nice, the n cancels, so this thing is 2 over pi, and then pi over 4, and this thing pi's cancel is 1 over 2. You see, the limits match. You can do it that way. You can do it taking the limit of n going to 0 of that. It's much safer usually to do it directly, independently. Because if you do it independently, you're sure that you don't have to deal with limits. It will make your life easier. All right, trick number 1. Trick number 2, I mean, this one was not a trick, more a subtlety. Trick number 2, doing Fourier integrals fast. I'll give you a couple of directions about using parity to do integrals fast. Let me erase. All right, so let's talk about parity of a function, in this case with respect to 0, but it could be through any center of parity. So imagine that I have here 0, right? And then a function that is, for example, let me write this function. This is t. F of x equals t. It's a straight line. All right. So this function has parity. It's odd. What do I mean by odd? I mean that, well, f of minus x is minus f of x. So if I go, this is the same as saying f of minus x equals minus f of x, right? It's the same thing. Multiply by minus 1 both sides. You can tell that f of 1 is 1, and f of minus 1 is minus 1, right? So t is an odd function. Now, if I were doing the integral from here to here of the function t, it would be this area plus this area, negative, positive, they cancel. The integral of an odd function on a symmetric interval, taking the center of symmetry, the point of parity, the point with respect to which is odd, is 0 always. And what happens if it's an even function? Let me write an even function instead. So I can do t squared. T squared is a parabola, right? So t squared would be something like that, right? T squared. Now t squared is even. If you take here, for example, 1 and minus 1, in both cases it gives you 1. So in this case, f of minus x equals f of x. If it's even, like any even polynomial with no independent term, if it's even, then the integral from minus a, that I do the integral from minus a to a, this area plus this area is the same area, so I can write as twice the integrals from 0 to the end of the interval. So far, so good. Now, parity of functions, if they have a parity, you can have a function that is neither even or odd. For example, t plus t squared is neither even or odd. But oftentimes, you will have functions that are define parity. The sine and the cosine have defined parities, indeed, the sine of x is equal to the minus sign of minus x, so the sign is odd, and the cosine of x is equal to the cosine of minus x, so the cosine is even. Now the parity of functions and their product works like the sum with numbers. If I have an odd number and I add another number that is odd, I get an even number, right? 3 plus 5, 8. Odd plus odd, even. And now, even plus odd, right? When I sum numbers. Well, with functions, it's by multiplication. So, let me erase this quickly. If a function, let me write it like that. If I have the function f of x equals an odd function times an odd function, where O of x and O prime of x are odd, then f of x is even. The product of two odd functions is even. The product of two even functions is also even. Okay? Ex, E prime x are even. And finally, the product of an even function and an odd function is odd. All right, that's the way it works. So an even function times an odd function is an odd function. So, for example, if I have t squared times t to the 4, those are even functions, so t to the 6 is an even function as well. If I have t, which is odd, times t squared, I get t to the power 3, which is odd. So odd times even is odd. All right, how does that help us? Here we will always be doing integrals in full periodicity intervals, as we will see, and the sine is an odd function and the cosine is an even function. So if f has definite parity, we know that the integrals will be either 0 or just twice the integral from 0 to the end of the interval. Hopefully this is clear, but we will be using it in examples and you will be seeing how we use it, and that will save us from actually doing integrals. We can do it, applying this when you practice a couple of times is 1 second. Oh yeah, that's 0 because it's odd. All right, and you will see how you actually gain that skill super fast. All right, let's see the last bit of this block, which is let's go beyond the limitation of minus pi to pi that Fourier originally gave, and let's talk about periodic functions of any periodicity. All right, let's do it. So here we go, the extension. The Fourier series for periodic functions of period capital T. Let's do that. We are going to be able to give an expression as a sum of sines and cosines of functions that are periodic. Any kind of function that is periodic, that is piecewise continuous, as we saw before. So consider a piecewise continuous periodic function, f of t, and this means periodic. F of t is equal to f of t plus t. That's periodicity. It repeats itself after t units. And the period, we write it in terms of this omega. This is the frequency, or you want to call it angular frequency. Keep in mind, the physical units, oftentimes you will hear, oh, frequency has units of second minus 1 hertz, and angular frequency has units of radians per second. No, for a physicist, radian is not a unit. The units are still seconds minus 1, because radians have no units. What is a radian? It's the relationship between a radius and the arc, right? And it's length divided by length, has no dimensions, no units. Radian, the unit, quote unquote, of angle is not a thing that has units, all right? So angular frequencies are also measured in hertz. Anyway, you often read above in engineering radians per second. It's really not a unit, radian, just to keep it in your mind. Okay, it's 8-dimensional. All right, anyways, so we write the frequency in terms of the angular frequency, so the period is 2 pi over omega, okay? And then we say, the Fourier series representation for this function, so the function is exactly equal to a0 divided by 2 plus the sine of an cosine. Instead of n, now it's n omega t plus bn sine n omega t. Remember, when the period was minus pi to pi, the period was 2 pi. So if the period is 2 pi, then omega is 1. And that's why in the past there was nx and an x in here instead of n omega x, or t in this case. I changed the variable on purpose. All right, so you see that this is the general one. This generalizes what we saw before for the interval minus pi to pi. All right, and now the inner products that give me the an and bn coefficients are 2 divided by the period and an integral from t0 to t0 plus t, the function times the cosine integrated, and bn, the sine coefficients, is 2 divided by t, integral from the t0 to t0 plus t, ft sine n omega t dt. What is t0? Whatever you want. What makes the integrals easier? Because the function is periodic and it repeats itself. If you pick one length of one period, no matter where you put it, it's the same integral. So t0 is your choice. It will be correct no matter what value of t0 you choose. It will be the same integral, the same result, because of the function being periodic. All right, let's do an example. Let's compute the Fourier series for this function that I wrote in a little bit bizarre way, so we learn how to decode and draw it. Always draw the function, always draw it. All right, we have this function that is 1 if t is between 4n and 4n plus 2 when n is an integer, and 0 otherwise. Let's identify the values of t for which this function is 1 and for which ones are 0. All right, let's take first n equals 0, the first one. For n equals 0, this means t between 0 and 2. Okay, so between 0, which is here, and 2, the function is 1. Let's write it here. Let's go up. Right, so this function is 1. Okay, wonderful. All right, that happens for n equals 0. Now, the next time, let's take n equals 1. When n is equal to 1, is between 4 and 6. So between 4 and 6, this is 1, right? This is also equal to 1. Wonderful. Let's take n minus 1. When n is minus 1, this is between minus 4 and minus 2. All right, so between 4 and minus 2, the same as this, and so on and so forth, right? We see how it goes, and 0 otherwise. So this function is, this is a little bit crooked because this is my drawing skills, right? Anyway. All right, so we get, and this is the height is the same for all of them. It should be the same for all of them, which is 1. All right, all right. So this function is periodic, as you can tell. It repeats itself. And the unit of period is, for example, from here to here. My drawing skills, sorry about that. This is the period, right? So it's this thing repeated to both times. This is the period t, if you want. So we can tell that t is equal to 4 in this case. So t is 4. The function is periodic with a period 4. Wonderful. All right. What does that mean? Well, that means that omega, right, if t is 4 with this formula, so as we have here, omega in this case is pi over 2. All right. So it's t divided by 2 pi. I do the inverse. Okay. So omega is pi over 2. And we can do the Fourier series. How do we compute it? Well, again, the first step is computing A0. So this will take several steps, and there's one complication, and we will be dealing with it as we go. All right. So A0 first, the easiest one. A0 is 2 over the period. Okay, 2 over 4. And an integral. What do I take as T0? Well, let's take from 0 to 4. We could have taken minus 2. From minus 2 to 2 would have worked. From 0 to 4 also works. So let's take from 0 to 4, for example. Of f of t, and then cosine of 0. So it's just f of t dt from 0 to 4. Okay. Now, what is the integral from 0 to 4? If we do it, we see very clearly that is 0 from 2 to 4, so this is the same as, this is also an even function. We could have done it like that, but anyway, whatever. Let's do it as we have. This is 1 over 2 from this integral from 0 to 2 of 1 dt, right? So this thing is actually 2 divided by 2 equals 1. A0 is 1. Wonderful, we have A0. What about AN? Okay, let's do AN. AN is the integral from, so it's first 2 divided by 4, the integral of f of t from 0 to 4 cosine of n omega. And what's the value of omega? Pi over 2. So n pi over 2 times t dt. Same as before, we get 1 over 2 integral from 0 to 2 of 1 times the cosine of n pi divided by 2t dt. The integral of the cosine is the sine, and then we have the coefficient n pi over 2 that gets inverted, so we get 1 over 2 and then 2 n pi, all right, and then we get the sine of n pi over 2 t evaluated from 0 to 2. All right, so this thing is equal to, maybe I can write it here. The sine of, when it's 2, is the sine of 2 pi. Oh, so when t is equal to, this is the sine of n pi. And when it's 0 is the sine of 0. The sine of n pi and the sine of 0 is both 0. So I can write, maybe I'm going to shorten it a bit. All right, so I compressed it a bit. And this is the 2 cancels. So 1 over n over pi. And then we get the sine of n pi, well, I'll write it, sine of 2, where n is a sine of n pi, right, when t is equal to, minus the sine of 0. Oh, but this is 0, and this is 0 for any n integer, this is 0, and for 0 is 0. So the whole thing is 0. All right, so an, I'll write it here, an different from 0 is equal to 0. All right, so this is the result that we got out of this calculation. A0 is 1. I mean, I'll collect it here. How about it? I'll collect it here. A0 is 1. An larger than 0, it's equal to 0. So I have these 2 coefficients here for the a's. Let's compute the b's. All right. Now the b's. Bn, it's equal to 2 over 4 integral from 0 to 4 f of t cosine n pi divided by 2, sine n pi divided by 2t. Okay? All right. dt. All right, so we do the same as before. This is 1 over 2 integral 0 to 2, because the function is 0 from 2 to 4, of 1 times the sine n pi divided by 2t dt. And this is equal to, again, same as before, 1 over 2, and then 2 divided by n pi with a minus, because the integral of the sine is the minus cosine. All right, and then I get the cosine of n pi over 2t evaluated from t equals 0 to 2. So if we simplify a bit, we get 2 cancels, minus 1 divided by n pi, and then I get the cosine of n pi minus the cosine of 0. Now, what is the cosine of 0? The cosine of 0 is 1. What is the cosine of n pi? This is important. This will appear many times, so please pay attention to this. What is the cosine of n pi? So if we draw it, right, this is the cosine of 0. This is the cosine of 1 pi minus 1. The cosine of 2 pi plus 1. The cosine of 3 pi minus 1. The cosine of 4 pi, 1. So it's alternating between minus 1 and 1. So this thing here is minus 1 to the n. All right, super important. And I know that you're not used to it. Now, let's see. Let's do the following. Then I'm going to write this as follows. Bn, because simplifying this is an art, okay? Bn, it's equal to, I'm going to put the sign inside, 1 over n pi and then I get 1 minus 1 to the power of n. Okay, that's the n. Now, that is correct, but it's not simple. And it's not simplified at most. And you won't get full marks with this, because for full marks you need to give the simplest expression for all the things that regard with Fourier series. So what I realized is that Bn is equal to what happens when n is even, and what happens when n is odd. When n is even is 1 minus 1, and therefore is 0 for even n. And what happens when n is odd? When n is odd, this thing is 1 minus 1, which is a 2 in here. So it's 2 over n pi for odd n. Okay? All right, and this is important because, so this is Bn, this is the simplified version of Bn. When we write the series, this is going to be really important, all right? So pay attention to what comes next. We got the A0 equals 1, the ANs different from 0 are 0, and the BNs are 0 if n are even, and 2 over n pi if n is odd, okay? Now let's write the series. Let me erase everything that is not the expressions of A and B. All right, so I erased, I put the solutions for the coefficients A0, AN, and BN here. And let's write the series. The series tells me A0 divided by 2, well, so 1/2. All right, plus there is no cosine terms. Wonderful, so I have only sine terms. N equals 1 to infinity, Bn sine. I have to remember what the omega was here. Omega here is pi over 2. Okay. Remember always that omega, let me just write it here, is 2 pi over t. In this case, omega is 2 pi over 4, that was the period, right? So it's pi over 2, okay? And that comes from here. All right, sine of n pi over 2 t. Now, I cannot just blindly, I mean, I could have taken the b with the 1, so remember the expression that we had for the b. We had the expression, we had Bn, it's equal to 1 over n pi, 1 minus 1 to the n. I could have taken this and put it here, sure. And put it here as well, sure. It would have been a horrible series, but it's not full marks. Why is it not full marks? Because it can be simplified. You are adding an infinite number of terms that are 0. Keep in mind, all the even ones in here are 0. So what we need to do is to convert it to a sum that doesn't contain the even ones, all right? You're not very used to doing that. We're going to do it a bunch of times, so don't worry too much. Pay attention to what we are going to do now, okay? Now, the first thing I want to do is take out, I'm going to do a change of variables that only takes the even. I know that the even ones are 0 and the odd ones are not 0. So let me split this into two sums. This thing is equal to 1/2 plus the sum L equals 1 to infinity B 2L sine 2L pi over 2t plus another sum M equals 1 to infinity B to M minus 1 sine 2M minus 1 pi divided by 2t. What did I just do? Well, I separated the even terms from the odd terms. And this is the same sum. This thing is equal to this. Let's check. Here I go from B1, sine of 1 times pi, B2, sine of pi over 2, 2 pi over 2, B3, 3 pi over 2. And here I have, on this side, when L is 1, B2, when L is 2, B4, B6, B8, this one only runs over the even values of the subindex of B, you see? N equals to L only runs through the even values of the subindex of B. Whereas here, when N is equal to 1, B is 1. When N is equal to 2, B is 3. When N is equal to 3, B is 5, B5, right? And then sine of 5 pi and so on. So this is exactly the same sum, and I separated the even terms from the odd terms. Now, of course, L or M are dummy indices, they're summed. I could call it Joshua if I want. I could call this one Joshua first, and then this n. I could give it whatever name I want. And in fact, I could do this. And now it's n. You see the index, I can give them whatever name I want. I could repeat n if I want, because they're separate sums. All right, so there you go. We got all the even terms here, all the odd terms. Now, the nice thing is that I know that all the even terms, when the subindex of n is even, then this is 0. When the subindex of n is odd, it won't be 0. But I need to transform the variable. I went from n to 2n minus 1. So I need to write here dn, it's equal to 2 over 2n minus 1 pi. I've done the change n going to 2n minus 1. And that change is what only keeps the odd terms in the sum. If I do that, then I get finally that f of t, it's equal to 1 over 2 plus sum n equals 1 to infinity. And now I substitute these terms, the odd ones. 2 divided by 2n minus 1 pi. All right. And this is, where's the rest? Here. Times the sine of 2n minus 1 pi divided by 2t. That's the result. We can simplify it a tiny bit more by taking factors out. F of t is equal to 1 over 2 plus, I take the numbers out, 2 over pi, sum n equals 1 to infinity of 1 over 2n minus 1 times the sine of 2n minus 1 pi divided by 2t. And that's the final result. That is f of x, the Fourier series representation of the function f of x, like that one. This function is that one. All right, I know that separating the odd terms from the even terms can be difficult. It helps perhaps, instead of calling all of them n at the beginning, you could keep calling it L or whatever, and then you say, oh, but I know then that I went from n to 2L minus 1. So when I see an n, I put a 2L minus 1, 2L minus 1, right? And then you write an L. Fine with me. But I want to stress, this is BL, right? But I want to stress that this is a dummy index. You can call it Joshua, you can call it n. This is something that with practice, you will get nailed down, but it's really important, it's part of the exercise, that you are able to separate the even, when you have that the even numbers, the half of the summands in here. It would be correct, don't get me wrong, to write the bn that you got before, the 1 minus 1 to the n and so on, but it's not complete, okay? If you want the complete one, you shouldn't be summing over half of the integers that give you 0. You need to separate the even and the odds, and the even ones are 0, and you just keep the odd ones, okay? And that's the final result. And again, keep in mind that once you've done the change of variables, you can call it back n if you want, because it's a dummy variable. So the substitution we did is n goes to n minus 1. N here runs over all integers, but 2n minus 1 runs over only the odd integers, right? When n is equal to 1, that goes from 1, 3, 5, this goes from 1, 2, 3, 4, this only goes 1, 3, 5, 7. All right, I hope it's clear, but if not, please bring all your questions to the review sessions, okay? And then we will do plenty of examples and we will see more of this, so I wouldn't worry. All right, this is the end of this video. In the next video, we're gonna see how to actually represent any function, even if it's not periodic, in an interval, by doing the 3 different kinds or usual kinds of Fourier representations that we have. What is called the periodic extension, the odd extension, and the even extension, also called periodic representation, odd representation, even representation, also called the sine Fourier series, the cosine Fourier series, and the mixed Fourier series. We will see that one in the next video. Until then, see you.